This chart is about motion diagrams, which is one of the tools we'll use for visualizing motion. It can be used qualitatively, which is what we usually will do, but it can also be, if carefully done, it can also be a quantitative portrayal of motion. So the idea with motion diagram is to show the position of the particle in constant increments of time, somewhat like movie clips. This first one here is showing constant velocity, and above each point I put the time, and so here is 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and I've drawn dots connected by displacement vectors, and so there's a displacement vector from 0 to 1 showing that the particle underwent that displacement for that time interval, and since all the displacements are the same, this is an example of constant velocity. If each one of these fine divisions were 1 meter, then there would be 1, 2, 3 meters between each one of these, and this particle would be going rightward at 3 meters per second. Here's another constant velocity one. This second particle is going with greater rightward velocity, but it's still constant since the displacement vectors are constant over 1 second time intervals. The time intervals can be anything you like. Usually in class and in the book 1 second is what's taken just for ease. This one has, on my graph division paper, 1, 2, 3, 4, 5 divisions, and if each division represents a meter, this would be going rightward with a constant velocity of 5 meters per second. This next one is a motion diagram for a particle going rightward but speeding up in a rightward direction. And you can tell it's speeding up in the rightward direction because the displacement vectors are getting longer for each subsequent time interval. So the average velocity from 0 to 1 second is 1 meter per second, again assuming that one division is 1 meter. And from 1 to 2 it's 2 meters per second, and the average velocity from 2 to 3 is 3 meters per second, and from 3 to 4, 4 meters per second, and etc. This next one shows a particle that's moving to the right but slowing down, and so it starts off with large displacements which get shorter as time progresses. Now the last two I have going horizontally are speeding up to the left, and so here we're going to start at the right end and go leftward. The displacement vectors to the left are getting ever longer and longer, and so therefore the particle is speeding up to the left, the velocity to the left is increasing. And the last one I have here is slowing down to the left, and this one starts with large displacement vectors, and then the displacement vectors pointing to the left get shorter and shorter. This one I have off to the right here is an example of a vertical one, and so you might get something like this if you took a paper cone like a coffee filter or something and dropped it, and just a moment after you drop it, an object like that at the kind of air we have at sea level, regular conditions, very quickly achieves what we call terminal velocity, and so here it is going at 2 meters per second in a downward direction, and again you can tell it's going at constant velocity because the displacement vectors are all in the same direction and the same length. So we'll use this quite a bit in the beginning and then progress to other ways of thinking about things, but this is a very good concept building tool.